All right. Today we're basically working back the other direction. So you'll be able to use our linear factorization, which we talked about at the end, where we set up the factors, and find the polynomial that would have given us the zeros that we are told that it has. So we have been handed a polynomial several times and said find the zeros, and now we're going to work our way backwards. These are the zeros. What would the polynomial have been? Similar to the process of like factoring and foiling. They kind of undo each other. And so what happens is we get a lot of these vocab words going on: zeros, factors, polynomials, and remembering what does our answer even look like if that is the question. So just kind of sitting them all side by side, because these tend to be our questions. Just a reminder that zeros look like numbers, right? So if the question is what are the zeros, our answer would just be a list of numbers. For example, like 1/2, -3, and maybe plus or minus 4i. Those would all be examples of zeros. Zeros can be asked of us also as roots, or to solve or find the solutions of. Those are all asking us the same question, and all our answers would look similarly, a list of numbers. Factors are listed with a parentheses and an X, right? That would be a factor, and that it is always the opposite sign of our zero. So examples of something that would be given as a factor would be like x plus 3 or an x minus 1 quantity squared. Those will all be considered factors. And like today's question is going to be, what are the polynomials? So polynomials, first of all, to have an answer of a polynomial, you will have had to FOIL at some point to get there. And also there are no parentheses. When you are done with a polynomial, we're not going to have a parentheses in there. Typically listed as like a f of x. What would an answer like that look like? Could look something like f of x equals negative x to the 4th plus 5x squared minus 7. Something like that would be an example of a polynomial. And just what those even look like. Now, they're all related to each other, so to get a polynomial, I would work through my factors. To get to zeros from a polynomial, I would work through my factors and set things equal to 0. All right, all related to each other. It's just what format it's asking us for the answer to be in. So let's look at it. We're going to be asked these questions in a couple different ways today. One of those is going to be something like this, where it says, given the zeros, write a polynomial of least degree. Because I'll tell you right now that given these zeros, we could write a whole bunch of different polynomials. If I were to like insert in some multiplicities in there, it would still have that list of zeros, but it would give me a higher order polynomial. And so what we're going to do is we're just going to say that we're going to pick the smallest multiplicity possible for each of these. Since none of these have a multiplicity listed, we would make it a multiplicity of 1, or raise each of these to the first. Okay. The 3 up there are very important for us to look at individually. The first one is very normal. If our 0 is -3, what would it have looked like in the factor? Plus 3, right? So first of all, reminder on using an opposite sign, right? To move from a 0 to a factor. Because the rule is, it is x minus the 0, and the minus the 0 part of it changes the sign on our 0, right? Okay, let's talk the fraction part of it. We're going to come over here and have a little sidebar on how to get fractions into into factors. So basically, we're going to work backwards. I had some factor here. I set what was inside of there equal to 0, right? And I solved, and in my solving process, I landed back at x equals 2/3, and then I added 2/3 to my list of zeros. So it's kind of weird to do it this way, but if I were to unsolve that and get it back to equaling 0, the first thing we would have done, or actually the last thing we would have done in our solving process, was to divide by that 3. So if I undivide by that 3, I would end up with 3x equals 2. Bring that 2 back over, I would have 3x minus 2, which means our factor would have been 3x minus 2. Okay, so what I want to look at is comparing the fraction to where those numbers end up in the factor. Okay, and you see where I figured that out is I kind of unsolved it, right? So I'm going to rewrite that a different order here. Given this, now knowing that we end up with this, right? That's what I just wrote up there. Look at where each of these things go. Your denominator moves to the number in front of x. Your numerator moves to the end. And we do the opposite sign, right? It is a positive 2/3, so we subtract. So it goes denominator, opposite sign, numerator. Right, there's your factor. Denominator goes in front of x, whatever your opposite sign is, numerator goes after when we are moving from a fraction to a factor. So doing that here, that 2/3, which we just did all of that work over here, would go to being 3x minus 2. Okay. The last one that is very important that we get out of this is, okay, well then what happens if in our list of zeros we have the number 0? What does that look like as a factor? It's not. It's x. It's x, right? So that's also a unique one that we need to look at. And I'm going to write that out front because we typically put just a plain old x sitting out front. It would have been a GCF that had gotten factored out. So again, remember what we're looking at right now. This is our list of factors. The question is find the polynomial, which means we need to FOIL to get there. So we have our list of factors set up, FOIL to get to your actual answer of the polynomial. When you have a GCF, I would save that to the very last thing I do. Distribute your GCF is the very last thing. So you'll see me start here and FOIL this, bring that x down. So if we FOIL that, what do we get here? 3x squared minus 2x plus 9x minus 6, which would be 3x squared plus 7x minus 6. Distribute that x through, and we get 3x cubed plus 7x squared minus 6x. That is a polynomial. Questions? Okay, that's essentially our process today. We are going to look at a couple different variations, obviously, on that, and then getting a little bit more specific of a polynomial based off of some given information. So let's look at one more here of this similar type so that we can see what happens when we have a multiplicity in our list of zeros. Same directions, given the zeros, right? A polynomial of least degree just means we're not going to make anything bigger than it needs to be. We move into our factors first, the same as we would have. So if it has a 0 of 1, remember opposite sign. So my factor would look like x minus 1. But what about that multiplicity of 2 squared, right? And remember specifically that squared goes on the outside of our parentheses. And then our other one, x opposite sign 4, so x plus 4. Remember that squared means I'm going to write that twice to FOIL. Now, let's talk about order of FOILing. If you don't have any imaginaries, it makes absolutely no difference what order you pick to FOIL. Pick the first two or pick the last two, it doesn't matter. And if you and your table partner pick different ones to start with, it doesn't matter. You will get the same answer at the end, just pick any two and start there and hold on to the last one until the end. So let's see, if I FOIL x minus 1 times x minus 1, I would end up with x squared minus 2x plus 1. And then when I'm taking a 3-term times a 2-term, remember you're just going to do one at a time. So if I take that first thing of an x squared, I'm going to distribute it all the way to that other one, which would give me x cubed plus 4x squared. And then I do that with my next term. Negative 2x times both things in there would give me negative 2x squared minus 8x. And finally, multiply everything by 1 plus x plus 4. And to finish up, combine your like terms. We only have in one x cubed term, so it's not going to change. I have an x squared here and here. Combine those would give me a positive 2x squared. Plain x here and here. Combine those would give me a negative 7x and only one constant, so that will not change. There is your polynomial. The only variation on the multiplicity that I don't have an example of in our notes to look at, so we're just going to look at a sidebar example here, is if in my list of zeros, I have these numbers sitting here, and I say that also we have a 0 with a multiplicity of 2, we now know that a 0 of 0 is going to look like an x sitting out front, but if it has a multiplicity of 2, I just square that, right? So the multiplicity of 2 part is what I'm talking about. Normally it would go outside my parentheses, but if it's just a plain old x, it just goes on the plain old x. Questions on that? Okay, continuing on to our other variations, we need to remember, or I'm going to help us with a bit of a shortcut here, because we're going to start getting into imaginaries, okay? When we looked at imaginaries, before I jump into this guy, when we were doing like rational expressions and we had something like a 3 plus 2i down here and something up here, and we used our conjugate to simplify that, you remember that word? And we multiplied by 3 minus 2i. Remember doing that? Okay. And we talked about, okay, yes, I can FOIL 3 plus 2i times 3 minus 2i to get to this shortcut. But when we do that, those middle terms will always cancel. And then we end up with minus 4, and I times I is I squared, which is a negative 1. And what we end up with is the first term plus, first term squared plus the second term squared, and that was always true. You guys remember that? That was a little bit of a shortcut, but it works. And if you can do that shortcut, it's going to help us today. So that's your first term squared. It's always plus because of the I squared. And that's your second number squared. Well, that doesn't change when it becomes x's. Okay, so what we're going to see today is this conjugate thing going on with like an x minus 7i and an x plus 7i. So if I FOIL this, yes, I can FOIL it the long route, but I can also try this shortcut that says it's going to be my first term squared plus my second term squared. So if I did that, this all multiplied out would give me my first term squared. Well, my first term is x. Squared is x squared. Plus, and then my second term squared, we're again talking about just the 7, just what's in front of the x. And 7 squared is 49. So there's your first term squared plus your second term squared. And if you understand that shortcut, it's just going to save you some time. And hopefully this makes sense why we have an imaginary. When I were to set this equal to 0 and solve, you always get an imaginary from the format of x squared plus a number, because we would subtract and then be square rooting a negative, right? So it should make sense that when we go to multiply those out, we'll always end at an x squared plus something. Okay, using that to help us with this next problem. Notice our question has changed a little bit. It says now, find a 4th degree polynomial function f of x with real coefficients that has -2, 2, and I as zeros. And then it gives us a little bit of extra information, which we're going to come back to later, that says f of 3 equals -150. So there's a couple things I want to point out in this. First of all, it says that it's a 4th degree polynomial. 4th degree polynomial means at the end of my problem, I'm going to have an x to the 4th, right? It also means that I should have 4 zeros. If I pull the zeros out of this problem, I have -2, I have 2, and I have I, and we need to bring back in something we learned yesterday that explains why I'm short a 0 right now. Does anyone remember what I talked about yesterday? If I have an I as a 0, imaginary zeros always come with their imaginary friends, right? So if I, any type of I, any type of complex number is on my list of I's or on my list of zeros, automatically that means that I also get its imaginary friend or its conjugate, negative I. We will have to add that to the list. They will never tell you both because it is assumed that you understand that every imaginary comes as a pair. Okay. So then from our zeros, just like we did earlier, we're going to go to our factors and then FOIL to get to our polynomial. So my factors would be x plus 2, x minus 2. And then what's unique to this type of problem is the imaginaries, x minus I, x plus I. I do have 4 parentheses up there, so I picked 2 and FOIL, but you can do 2 and 2 at the same time. So like I could FOIL these first 2 and FOIL the second 2 all at the same time. So x plus 2, x minus 2. Again, I could do the long route here, x squared minus 2x plus 2x minus 4, or recognize that that's a difference of 2 squares. My middle terms will cancel. We get x squared minus 4. Same thing with my imaginaries, is I can FOIL that. If I forget, I can FOIL and do x squared plus xi minus xi minus I squared. Ooh, I squared is -1, right? Or that shortcut we just talked about on the last page, when we are looking at conjugates of imaginaries, I always get the first thing squared plus, always. So it'll always be x squared plus. And then the second number squared, well, our second number is kind of weird on this one, but it's 1. And 1 squared is 1, which is where this plus 1 is showing up. We do have one more step here, and that is to continue to FOIL one more time, which would give me an x to the 4th. Let's see, plus x squared minus 4x squared minus 4. Or cleaning that up, we get an x to the 4th minus 3x squared minus 4. Now, you notice that I kind of left a little space in there, and that is because they give us specific information. So when they give us specific information, they're saying that, yes, that's the polynomial, but it is some multiple of it, meaning that we either like vertically stretched or shrank that polynomial to get this particular value at x equals 3. And so what we're going to do is figure out what that multiple is of this polynomial specifically. So now I plug in this information. Is that x? Remember, this is x equals 3 is going to go in for the x's in my polynomial. And they say when I do that, I'm going to get an answer of -150. And to do that, we have to figure out what this multiple right here would be when I plug in 3 for x. Does anyone recognize this one? Wasn't this like our warm-up yesterday? Told you it was going to show up, didn't I? Yeah. So cleaning this up, I know it cleans up nice because we did this one yesterday. 3 to the 4th is 81. This is where I'd be grabbing my calculator. 3 squared is 9 times -3 is 27, which when we put all that together, we got 50, right? And right now they call it a sub n. You can call whatever variable you want. B, Z, C, pick a variable. I don't care if a sub n bothers you, but now I'm just dividing by 50 to figure out what that variable is. And it's -3. So to finish out our problem, I'm going to go put that back in here and distribute it through to figure out our specific polynomial. And I understand that this is a lot of work here, but that's because I'm showing every last little step. You guys absolutely can speed this up. Yes, we can skip some of these showing all of our work steps. But our official polynomial that would go through this point right here would be -3x to the 4th plus 9x squared plus 12. Questions? We're going to practice that one more time here, and then we'll see one last little variation on these types of problems. So same type of directions at the top here. Find a third degree polynomial. So again, that tells me biggest exponent is a 3. My list of zeros should have 3 numbers on it. With real coefficients that has -3 and I as zeros, such that f of 1 equals 8. So I'm going to start with my list of zeros. I have -3 and I. What am I adding to this list? It's the imaginary friend, -I, right? Put those into my factors. Now here is my practical piece of advice for you. Earlier, if you heard me say this, is I said when we have multiple parentheses, the order that you multiply those in does not matter. And that is true. However, if you have imaginary conjugates in there, start there. It will make your life so much easier. So I would never pick to FOIL these first 2 because those are not imaginary conjugates of each other, right? Pick the imaginary conjugates, always start here. It will be so much easier if you do. Okay, and let's try our shortcut here. If it is x minus I and x plus I, first thing squared, plus the second thing squared. When I FOIL that, first thing is x, so first thing squared, plus, always plus when it's imaginaries. Second thing squared, this is the same one we just saw on the last page. 1 squared is 1. Questions? Keep FOILing. X cubed plus 3x squared plus x plus 3. And that is our generic polynomial, and we're going to figure out what multiple of that we get with that specific information. So I'm going to bring that up here and say, okay, f of x equals sum a sub n times that. And at this point, I'll plug in 1 and set it equal to 8. Okay, so 1 cubed is 1, plus 3, plus 1, plus 3 is 8. We get the a sub n equals 1, which means when I go to plug 1 back in there and distribute it, is it going to change my polynomial? 1 times all of that is not going to change it, right? So we can jump straight to our polynomial, just that's a 1, which I don't need to write. X cubed plus 3x squared plus x plus 3. Questions? All right, you are on your own on this one. The question changed a little bit, but I want you to see exactly what it's going to look like when you see it in your book or on your worksheet today. N equals 3 is referring to the degree. Okay, and then it says 4 and 2i are zeros, and then it says f of -1 is -50. Try getting all the way to the end on your own. You are going to be very frustrated with the problem if you do not remember the imaginary friend, okay? Every time you are given an imaginary, add to the list the conjugate. So I automatically add the negative 2i to my list. If you do not, you're never going to get rid of the i's, and that's going to seem weird. And you should always get rid of the i's, okay? So if you are stuck with i's in your problem, something's wrong. Go back and try again. I, again, will always start here. If you forget to start there, you're going to have some ugly work ahead of you. Start with getting rid of your i's by multiplying the conjugates. First thing squared plus, imaginaries, it's always x squared plus 2 squared is where I get a 4 here. So if I forget that, just go back and FOIL. Keep foiling. Okay. And then we make this specific to what they gave us. So now I'm going to have some constant multiplier a sub n out front. Plug in -1 and set it equal to -50. All right, so this would be -1, -4, -4, -16 for a grand total of -25. And a sub n I see equals 2. So writing out my answer. I need to distribute a 2 through that polynomial, and we would get 2x cubed minus 8x squared plus 8x minus 32. Any questions? The last part that we have today is no different as far as once we start our process than what we've seen before. It actually is a little bit less work, but we have to recognize how to make it less work when we get there. And that is when we are given something like this. It says an incomplete picture of the graph of this function is shown here. And it's the function 2x to the 4th. So we're going to pretend that we don't have a calculator. I could go through my list of plus or minus p over q's or plus or minus factors of 36 over factors of 2. That list would be incredibly long. 36 has a lot of factors, okay? But I don't have to. Based on the fact that they gave me a little picture, it's not the whole picture of the whole graph, but based on the fact that they gave me a little picture of that graph, what can I learn from that? I can learn 2 zeros, can't I? So instead of going and typing this into my y equals and looking at the table, understand that zeros are also places that my graph hits the x-axis. And so I can see that I have a 0 at x equals 1. I can see that I have a 0 at x equals 3. So had I gone and typed this into my table, those would have given me answers of 0. And so I don't need a table. I can go to my synthetic division right now. And I know that when I use the ones that I'm seeing in my picture, I'll still get a remainder of 0 and work my way down to something that is factorable. Okay. Now, I'm going to pause here for just a second. Yes, I see another 0 up there, but can I have a conversation with my good number sense people real quick? Do you see that right now we'd be at an x cubed, but do you see that that's also factorable by grouping? If I factored out a 2 here, I'd be left with 2, 1, and 2. I would factor out a negative 18 here. I'd be left with 1 and 2. It's actually factorable by grouping. You could stop right now and just factor to find the rest of your answers. I just want to point that out, okay? I do actually know another answer though, so I'm just going to do a repeated synthetic division with that other 0 that works. Still should expect a remainder of 0. Which I get. And now I'm down to a quadratic, and I can go to my polynomial, and look to either factor or quadratic formula to find the ones that are missing that I couldn't see in our picture. Always look for a GCF. It will help you. It does not change your answer when you are solving, but it might make them smaller numbers to work with. Factors of 6 that add up to 5 would be 2 and 3. Setting those equal to 0 to solve. My last answers would be -2 and -3, and there are all 4 of my answers. So we were asked to find zeros. So we'll say zeros. Are 1 and 3 from our picture, -2 and -3 from our work on the side. It did ask us to draw a complete graph. I'm going to do this super fast, okay? Zeros at -3, -2, 1 and 3. I can see that my x-intercept is up at about 3.5 here. And my end behavior, positive, even. All my multiplicities are 1, so it would cross through. Positive, even, ends are going to head up. So I know it's going to cross through, cross through, cross through, cross through. There'd be a very fast version of that graph. Questions on that? Remembering all those things that we put together. All right. You actually do get a worksheet today. It does have a place on Google Classroom to submit it already. So when you are done with it, you will take a PDF scan and submit to Google Classroom.